This is Project 6, video number 1, pencil and paper part. Get a rubber ball. Being released from rest in water. We're going to need a free body diagram. Let's get started with that. We'll draw the ball. It's got a gravitational force acting on it. F sub g equal to mg. It's mass times the gravitational force constant. There's going to be a buoyant force acting on it. It's going to be accelerating upward. And there's going to be another retarding force, F viscous, which is equal to CV, where V is the velocity of the object. So we do a sum of the forces in the upward direction at any instant while it's already moving upward. Is going to be equal to the mass times the acceleration in the upward direction. And let's see, the sum of the forces is going to be FB minus FG minus FV is equal to MA. The buoyant force. This thing is totally submerged. So the buoyant force is going to be the mass of the displaced water times g. By Archimedes' principle, it's just the weight of the displaced fluid, which will be the mass of the displaced fluid. In this case, the fluid is water, so mdw times gravitational force constant. So that's equal to the density of the water times the volume of the ball, because it's totally submerged, so the volume of the displaced water is going to be equal to the volume of the ball times g. So this is all like an aside. And let's see what they gave us in this one. So we got the mass of the ball, and we got the diameter. So we got enough to get the density, and essentially we got the volume right there. Yeah, we got the volume from the diameter. So let's go ahead and replace that with, this is the density of water times 4/3 pi r cubed times g, where r is equal to d over 2. So I think I'll go ahead and substitute that in there. This is equal to density of water times volume of the ball, which is the volume of the displaced fluid, 4/3 pi times d over 2 quantity cubed, and then times g. So that's an 8. 4/8 is a half, so you got a 6 pi d cubed over 6. Call it pi over 6 times d cubed times g. Alright, that's the buoyant force. That was all a side issue. The gravitational force is just m mass of the ball times g. I use m sub b for the mass of the ball. And the velocity dependent force, or the viscous force, is c times v. Okay, FB minus FG. So we got rho times pi over 6 d cubed g That's FB minus FG minus M. I'll just call that the mass of the ball, times G minus C times the velocity is equal to MA. So A, this is interesting. I think I did a little extra work there for the buoyant force. I think I'll use an earlier expression. So the buoyant force is rho W V times G. Forgot the W anyway. Rho W times V times G. If I want to use that expression, I can, but I think I'm not going to want to, because this is rho, the volume of the, oh, this is the density of water. Let's not forget that. Volume of the ball, I'm going to divide both sides by the mass, so that's the volume times the mass times G minus M, well, that's the piece that I'm dividing both sides by, so minus C over M times the velocity, and that's equal to the acceleration. Okay. M over V is the density of, I think I'll divide top and bottom by V there, so it's more obvious what I'm doing here. Is rho W times V, times 1 over M over V. This is the volume of the displaced fluid, but it's also equal to the volume of the ball, because the ball is totally submerged. So times G minus C over M times little v is equal to A. So this is rho W times 1 over the density of the ball times G minus C over M times V equals A. So A is equal to, I'm going to go rho W over rho B, density of water divided by the density of the ball, minus 1 times G minus C over M times V. Okay, we got one of these situations where the acceleration is going to be continually changing, because you release it from rest, the velocity is continually changing. And so we're going to have one of these things that we want to create a table and step through. So I'm going to set a time step. I'll call it delta T. Oh, by the way, I guess I need rho B is let's go ahead and get rho B. I can do that first. So rho B is equal to the density of the ball, is the density of the ball, so it's the mass of the ball divided by the volume of the ball, which is the mass of the ball divided by 4/3 pi d over 2 quantity cubed, or it's the mass divided by pi over 6 times d cubed. And yeah, I think what I want to do is calculate that separately and then use the result in my nifty expression down here. I like to look at this the look at this, the look of this expression with the ratio of the two rows. Okay, so delta t, I'll make a small time step and see if we have to change that. 0.01 seconds. And then I create an n, which will just go 0, 1, 1, 2, etc. The time is n times delta t, and that'll just always be the case. So in other words, I'm going to have some integer to characterize all the rest of these variables. So this will actually be t sub n. And let's see what I want next. I'm going to define upward to be my positive direction. So I've got a coordinate system, call it the positive y direction, and the ball is moving along there. Everything is positive upward. The ball starts out, y0 is equal to 0. So the ball goes up that way. I'll indicate that with the dashed line there. And V0 y, but y is the only component we got, so I'll just call it V0. The y component I'll just call V0 is equal to 0. I think that's probably enough. So with that coordinate system, I go y sub n, and I go, the 0th one is just 0. V sub n, zero, and a sub n will be this expression, which with v is equal to 0, it starts out just being equal to that. But I think I'll write down the whole expression. So it's rho w divided by rho of the ball, the density of water divided by the density of the ball, minus 1 times the gravitational acceleration due to gravity, so it's a gravitational force constant, minus c over the mass of the ball times how fast the ball is going. Alrighty. Then in the next line, I want y of n of n to be equal to y of n minus 1, so that'll be this I, which is 0 for the first one, plus v sub n. And you know, I think that means I want to calculate these two in the opposite order. I guess it doesn't matter. I'll go ahead and write it down and then say what order I calculated it in. So v sub, I'm going to try v sub n times delta t. That really means I got to calculate v sub n first. Yeah, let's do that. So I'm going to go v sub n and y sub n. So 0, 0, and then here we say v sub n plus 1 is, or v sub n is v sub n minus 1. So the previous value plus a sub n minus 1, the old value acceleration, times delta t. And y sub n is going to be y sub n minus 1 plus v sub n, so I use the one that I just calculated, times delta t. And then this will just be what it was before, so ditto marks. And ditto marks for the next one. So for the v, I use the previous v, the previous a times delta t, and then I'll calculate the new position this way. So I think that's a pretty simple table, and I believe it's complete. And it's a way of dealing with this fact that the force depends on the velocity, which is continually changing. So for each trial we do this. Turns out it takes 2.38 seconds. And they're looking for c. So we're going to give it a value of c that we use to calculate this. This is the plan. We just write a function that takes the value of c and calculates all these quantities repeatedly up until y sub n is equal to the value that they said. 32.70 centimeters. Okay, I got to think about what the y final is. So y final I think what I'll keep track of is the top of the ball. So when the top of the ball first gets to the surface. So my reference line, this is my y0. Reference line. And so this is y final up to here. I think I'll call this D for the depth of the water. So y final is equal to D minus the diameter of the ball. So in other words, the top of the ball first gets to the top of the surface after it's traveled a distance equal to the depth minus the diameter of the ball. Okay, and the depth is given. So I think I got my plan for this project. I'm going to say things, initialize variables. D, the depth of water, capital D, the diameter of the ball. I need G, rho sub W. I'm going to calculate rho sub B. The density of the ball. What else? What did I need to calculate that? The diameter. Oh no. Put it all the way up here. Just the diameter and the mass of the ball. So let's see if I got the mass of the ball yet. So in other words, just set them equal to the known values, or assign these symbols the known values. Take C as an argument, and then I think what I want to do is set the values of T0, V0, Y0, and A0. And then do the while loop. Do a while loop. Init T. Oh, what do we need to? We don't need to graph anything. So T V X and A to time 0 values. And then 5 while, I wanted to call this Y, not X. Y is less than or equal to Y final. Which I'll calculate is just the depth minus the diameter. Calculate all those things. Calculate. Ooh, I think I want to bump I think I'll call this step 5, set n equal to 1. Alrighty. Calc T, I think I'll call it T of n, B of n, Y of n, A of n. Table above. And I think that's it. So end that while loop. Return T sub n. I think that's all our function is supposed to do. And then it's up to the user to use the function to find the answer. So, rubber ball, that mass at diameter takes a certain amount of time to get to the surface, which has been measured to be 2.38 seconds. Apparently they got some uncertainty in that value, but they didn't give it to us, and we don't care about it. Find C. Okay, so I really have very little idea what C is. I'm going to assume it's got units of newtons per meter per second. Newtons per meter per second. So the meters per second are in the denominator. So the F sub V, the viscous force, comes out in newtons. I might need to change this if I program it up and find that it doesn't work, but for now I think I've got a plan. I might have forgotten to initialize something, but when I go to program it, I'll come back and fix this up. So I think I got a comma in there that is not appropriate right now. So go ahead and erase that. But other than that, that marks the end of project number 6, video 1.